we've never seen before. There's no filter like this in analog. Okay, so this is uniquely digital filter. It's called a comb filter, and you're going to see why in a few minutes. Why it's called a comb filter. Okay. Does somebody have the mic open? Mr. Kerr, please close your mic. Thank you. Okay. The transfer function of this this comb filter, an example of a comb filter, this is not the only comb filter, is given. And this is example 716 of the textbook. Of course, we want to find the frequency response of it, and we just substitute, when we see Z, we substitute E to J omega. Right. And then, of course, we can expand the complex exponential into cosine and sine terms. Right. So when we do this, we have the square root of 1 minus 0.5 cosine 8 omega squared plus 0.5 sine 8 omega all squared. Give me a second, please. When we plot that, we get the top diagram. And that's the magnitude response. Okay. It should be obvious from this plot why it's called a comb filter, because it has peaks like you find in a comb. Okay. Now, because of these peaks spaced periodically, right, that has a special effect on a pulse. And if we go down, we'll see that. The middle diagram is our input signal. That's the input to a comb filter, and the output is in the bottom graph. Can somebody tell me what they see in the bottom graph? What happens to this pulse on the input?
It starts at 1 and then goes to 0. Like it goes down, eventually gets to 0.
All right, that's a very simple description that does not really capture what is happening. Look more carefully. What you're saying is true, but it's not. It doesn't fully describe what is happening. You're missing the key thing that's happening.
It's descending whilst the value of n becomes greater.
Yeah, well, that's what Mr. Johnson said. Look carefully at the input and look at the output. What is happening? you are getting delayed versions of the input. Isn't that obvious? And the shorter the delay, the greater the amplitude. So you get the original signal back. Okay, look at the input. You get the original signal back, and then a couple of seconds later, you get the same signal at half the amplitude, and then a couple of seconds later, you get another signal delayed now twice as much, but now we're at a quarter of the amplitude, and so on and so forth. What is that called? Where in real life you experience that? You get the original signal back, and then you get the resonance of the same signal.
I guess you have done like audio.
Be more specific. This is what echo is, folks. This is echo. You clap, and then you get the clap back a few seconds later, another clap a few seconds later, but that clap, the third clap is not as loud as the first and the second. And when the delays are short, it's not called echo anymore. It's called reverberation. It's called reverberation. When you sing in the shower, this is what happens. The tile reverberates your song, your singing, and you hear it as short echoes. And the song sounds fuller. This is the way they generate echo these days. When I was a technician, they had to do strange to get the echo. Echo was not an easy thing to reproduce. Now it's simply a digital filter. So this is what a comb filter costs us. A comb filter causes the signal to appear later, but at a small amplitude. Let me give you another example. This is the top graph is hello. It's just somebody saying hello. We sample somebody saying hello, and we put it in a wave file. And these are the digital values, and we plot digital value versus amplitude versus n. Basically, amplitude versus time. That's the original signal. That's just hello. The bottom graph, we put through a comb filter. I'll show you what that comb filter is in a second. And you see it says, hello, hello. We get an echo. The second part of the graph looks just like the first part of the graph, except that it's reduced in amplitude. And the filter we use for that one is given at the bottom. So you see the delay. The delay is like 6,499. That's a huge delay. But it has to be, because look where the original signal ends. The original signal ends is about n equals 7,000. So it's not surprising you have to delay it that much. So you now know here's another one. This one has This recursive filter has something on the numerator and something on the denominator. And when we find the frequency response of that and plot it, we get figure 717. This will also create echoes. Any questions about the comb filter? So here's something you could do in digital quite easy that you can't do in analog. You could create a filter that mimics reverberation. All right. We're talking about equal ripple filters. And from 410, you should know this from 410 actually. Okay. We may have a response that does this. Okay. Something like this. Okay. And here's 1. Right here is 1 plus delta. And here's our color frequency. Our color frequency here would be 1 minus delta, 1 minus ripple. And this frequency right here. This would be our cutoff frequency. That'd be our cutoff frequency. And here's the beginning of our stop band. And this level right here is called a stop band attenuation. If this is 1, and usually this is in dB. So that's 0 dB there. This is the magnitude. Well, this could be not digital. I mean, this is true of digital or analog filters. Okay. And the ripple, the deviation from 0 dB is called ripple. And equal ripple means this much is equal to this much is equal to this much. That's equal ripple. And this is called a stop band attenuation. This point here is a stop band attenuation. We did this in 410. 7 hertz. All right. So clearly right here we're approximating a low pass filter. What's this distance here called?
The transition band, no?
Yes, the transition band. This is called the transition band. Why? This don't work anymore. The transition band. Transition band. Okay. And from FS onwards, This is called a stop band. And this part here is called a pass band. Okay, I sent you a link. I sent you a link last night. Let me see if I can find it on my computer. So who am I missing? Mr. Pintard and who else?
Look like Dory.
Yes. All right. Okay. Let me share this with you. Before I do that, let me check this email, see if it's related to this class. Give me a second. I need to respond to this email.
Dr. Godric,
Yes.
which day is the final?
All right. I think I've said it many times. You could tell me. You could tell me. Can somebody else tell me what day is the final exam?
I believe it's the 22nd of November.
Thank you very much. The last day of class. All right.
I have the 24th written in my book, Dr. Carter. You may have to correct me on that, but I believe it's the 24th.
And I believe you're wrong. The
We don't have school on Friday, buddy.
Oh,
you see how poorly students listen in class? I admit, I did say the 24th initially, and then I immediately corrected it.
oh, I probably didn't hear that part.
I know, you don't listen. Well, so who's here? Everybody's here except Tori and Mr. Pindot. I'm going to send out an email later. Okay. But the problem is this: y'all don't read my emails. Okay. You don't read my emails, Mr. Anderson and Mr. Higgs made the very same mistakes I said not to in my email to the class. You just don't read my emails. And therefore, Mr. Higgs and Mr. Anderson.
Which mistake there was?
Mr. Adley.
I used 3 significant figures. my
You cannot use 3 significant figures because I'm asking for 4 significant figures. I've been asking for 4 significant figures since you knew me.
Oh no man, not 3, my bad. 4.
You
Don't
did
use
not
4.
use 4. Listen to me. Listen to me. You cannot work with 3 significant figures and end up with a 4 significant answer. That's impossible.
Dr. Cadre, I can assure you I did use 4 significant figures.
All right, Mr. Anderson. Let me look at your paper right now. Let me look at your paper. Let me look at your paper right now. All right. What's this? Okay. Cosine 1.8. Negative 0.227. Well, you got 1 here after that, but in fact it's 2. Okay, but let's go to the sine of 1.8. Sine of 1.8, 0.973. Is that 4 significant figures? 0.973. Is that 4 significant figures, Mr. Adley?
What's up? My bad.
You did not use 4 significant figures everywhere, and because of that, you get the amplitude wrong. I pointed that out in the email to you, and you ignored it. The magnitude should be 1.000, and your magnitude is 0.946. And the weird thing is, you use 3 significant figures in the phase, and you end up with 5 significant figures in your phase answer. How can you have 5 significant figures when you're working with 3 significant figures? All right. And looking at your paper, I see another error. I'll have to grade that again. There is no J. There is no J in the phase. There is no J in the magnitude. All right. Now I'm lost track of what I was doing.
You was about to bring up the pulse which you sent through email.
Let's see. Okay, this is it. This is it. Can you all see my filter on the screen? My filter graph on the screen?
Yes, sir.
All right. Here we go. So we desire the orange line. That's what we desire. We want 0 dB. We want 0 dB, but we want equal ripple about that. Okay? So we'll accept down here at the bottom left-hand corner, we'll accept 5 dB ripple, and we'll accept attenuation of -40 down here. That's how much attenuation we accept in the stop band. And right now we want the stop band begin at 500 hertz. And the pass band and the cutoff frequency be 400 hertz. Okay. And the sampling frequency is 2000. That's why the maximum frequency is 1000 hertz. And we say design the filter. And there it is. That's the design filter. Okay. See the ripple? See the ripple in the pass band? going up actually to 4.14 dB. And so the cutoff frequency will be at negative 0.414 dB. And you see the stop band begins at 500 hertz. Now, what do you see up here in the right-hand corner? What is this up here in the right-hand corner? What are these numbers? Well, folks, what do you want for a filter? What do you need to build a filter? What do you need to build a digital filter? Wow. All this work we did on filters, and y'all don't know what we need to build a digital filter?
Need a
Y'all don't. Go ahead.
sampling frequency.
We got the sampling frequency here. See it right here? Mr. Johnson, are you looking? Are you looking at my cursor?
Yes, sir.
Do you see where it says sampling frequency? It's down here, 2000 hertz. What do we need to build an FIR filter? Wow, all this math we've done, and you all have no idea what the math means. How do you create a digital filter?
Are you talking about what is required to make a digital signal?
No. I'm asking what does it require to make a digital filter? They have designed, look at the graph. They have designed a digital filter that has this magnitude response. And so I'm asking you, what are these numbers on the top right-hand corner? Clearly those numbers weren't there before they did design. After they did design, then those numbers are there. So these numbers are related to the filter. What numbers are these? All right. Since nobody can come up with what the numbers these are, tell me something. How do I create a moving average filter? What do I need to create a moving average filter?
Well, you need to have 1 over the amount of delays, so for example, and then open bracket. Then you'll have, for example, the different delays. So x of n would be a delay of 0. Xn minus 1 would be a delay of 1. I guess.
So what are you giving me, Mr. Johnson? This equation you're giving me, what equation is that?
The things on the right hand side in the input.
Let me go back to Mr. Johnson for a second.
That equation was for the moving average.
But like, is that the difference equation he's trying to give?
Thank you very much. A difference equation. To create a digital filter, you need a difference equation. To create any digital filter, you need a difference equation. You are implementing the difference equation. That's what you're implementing. Just like for analog filter, you're implementing a differential equation, but we don't emphasize that aspect of it. But for a digital filter, you must, because that's how you create it. We need the difference equation. For an FIR filter, where do we get the difference equation from?
The FIR filter, we got the difference equation from the impulse response.
Thank you very much. You see these numbers over here? That's the impulse response. This is n equals 0. The very top one, the next one is n equals 1. Let's plot the impulse response. See it there? See the impulse response? So we need the numbers of the impulse response. We need to know this number. That number is negative 0.020104, etc. This next number here is negative 0.058. That's a long number. I need this long number, otherwise you don't create the filter you think you're creating. See here, they're not using 4 significant figures. They're using a whole bunch. I didn't even count how many they're using. So there's the impulse response. We need the impulse response. What do you notice about the impulse response? What do you notice about the impulse response? The impulse response that is on screen right now, what do you notice about it?
It's fluctuating at different amplitudes and stuff like that.
Well, that's always true of any impulse response. If you don't have an impulse response that fluctuates, then what's the point?
It goes high at 0.005.
What I was trying to get from you is, how is this impulse response different from any other impulse response you've seen?
I mean, for me, this one's symmetrical.
Exactly. It's symmetrical about what? The 0.005 axis. See the 0.005 axis here? Okay. It's symmetrical about that axis. And that's true of these equal ripple filters. That's true of these equal ripple filters. They're going to be symmetrical. The impulse response is going to be symmetrical. Now let me give you one that I designed last night. Okay, there we go. There we go. Here we see the cutoff frequency is 300 hertz. We wanted a maximum ripple of 5 dB. We got that. Ripple is only 2.44. And I wanted a minimum attenuation of -30. And I got that. I got -34.55. Okay. And now here's the impulse response over here. Okay. We could plot that. And again, what do you notice? It's symmetrical. Okay. This is H of 0. This is H of 11. H of 0, H of 1, H of 2, H of 3, H of 4, H of 5, H of 6, H of 7, H of 8, H of 9, H of 10, sorry, H of 10, because they're 11 points. Right here, down here it says 11 taps, actual number of taps, 11. That's how you get the symmetry. You get 5 to the left and 5 to the right. So this is the impulse response. These numbers over here are the impulse response. So I copy these. I put them in octave. And I'm putting in octave. Let me find that file that I created at I don't know. Was it 1 o'clock this morning? Okay, what did I name that? Equal ripple filter. There we go. Okay. Yeah, see here? These are all the numbers that were created by that program. This is the impulse response. As a matter of fact, I'm going to plot that. The first thing I'm going to do is I'm going to plot that. Verify. Okay. Those are just the impulse response with just the fewer numbers displayed, but I'm still keeping the long number. And then I go to graph, and there it is. Wrong place. Okay. There it is. That's the same impulse response. And then I have to minimize this. And I have to tap a key. Okay. And there's I calculated the magnitude response. And how did I do that? Let's go back there. Let's go back there. Let me finish this a second. Okay. And so I tap it again and bring up the graph again. And there's the phase response. And again, it's linear. It's linear. Okay. This point here is negative 180, and this point up here is positive 180. Okay. We could do something called phase unwrapping. And this point here will continue down here, and we'll have one straight line. That's called phase unwrapping. But if you just ask for the phase, then the phase is not unwrapped. Now let me go to the code I wrote. Okay. So back here, y'all seeing the octave code, right?
Yes, sir.
All right. So here we go. Here's h of 1. Okay. Remember, in octave, there's no h of 0. So h of 1 is actually h of 0. H of 2 is actually h of 1 in terms of the impulse response. And then where we see z, we replace it what? With e to the j omega. Om is omega. This is actually h of 2. E to the minus j 2 omega. So all this is doing right here is calculating the frequency response. And then the next statement here is put that magnitude, the magnitude of that frequency response. ABSH is the magnitude of the frequency response. We'll put that in dB. And then plot it. And notice I have a pause. I have a pause after the graph. If I don't put a pause there, then the program will just run to the very end, and all I see is the last graph. I put a pause here, and when I put a pause here, the first graph comes on screen. Okay, I look at it, minimize it, and then tap my space key. And then I'll get the second graph. But all of this is from what? Me understanding what a digital filter is. Okay. The hardest part about this is coming up with the impulse response. I don't expect you to be able to come up with the impulse response of an equal ripple filter, because you don't have the math background for that. Well, I take that back. If I give you the frequency response, then you can come up with the impulse response. But if I don't give you anything for the filter, if I say design this equal ripple filter, and I don't give you anything, you can't do it because you don't have the math background. And not only that, even if you have a math background, we have to quite often use many, many H values. This one's just 11. And that ain't many. Sometimes you have to use up in the hundreds. So it's tedious, and you don't have the math skills. That's why I looked up that free software. But once they design the filter, they give you the impulse response because they know you need the impulse response to implement it. And you implement the difference equation. You implement that what? In software or in hardware. Remember, z to the negative 1, that means memory. Don't forget the block diagram of your difference equations. You are adding the delayed versions of the input to come up with the final output. We did all this, but apparently it was meaningless to you. You had no concept of why you're doing what you were doing. You are adding those delayed values together to create a filter. You can better see that in P-Spice. We did that with P-Spice earlier. Okay. Let me give you. Let me give you. So now, the very basic moving average filter, you know how to design. You know how to design that, but it's not a very good filter. It's not a very good FIR filter. Now you know there's something called an equal ripple FIR filter. But you can't design it without using software. And by design, I mean get the impulse response. Because you're adding stuff together. The difference equation is what? You need memory. You need memory. You need memory. Okay? This is H of 0. This is H of 1. This is H of 2. This is H of 3. This is H of 4. And all these zeta negative ones are memory. Either memory in software or memory in hardware. H of 5. And this continues. H of 6. And this goes all the way. H of 7. H of 8. H of 9. H of 10. So you need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You need 10. You need 10 memory devices. That filter we just looked at. You need 10 memory devices. And you have to add that to that to that. And all this is gain. Okay. This is H of 0. This should be better H of 1. I forget now how we did the game. Yeah, we did the game with triangles, I think. There's H of 2, but not in your software, because in your software, Octave or MATLAB don't like H of 0. It's H of 1, H of 2, H of 3. And you bring all those together. You bring all those together. And you add them together. That's what your difference equation says. And there's your output. There's X of n. And there's Y of n. And that's your difference equation diagram for a FIR filter. Any questions about this? So that's x of n. And this right here is x of n minus 1. And this is x of n minus 2. And this is x of n minus 3. And x of n minus 4. X of n minus 5. X of n minus 6. X of n minus 7. X of n minus 8. Okay. X of n minus 9. X of n minus 10. So what you have then is y equals x of n times h of 0 plus x of n minus 1 times h1 all the way up to h of n minus 10 times h of 10. Convolution, in other words, the output is x convolved with h. We talked about all this. So this is just like a moving average filter, except that your impulse response is not equal. And the moving average filter, all these h's are the same. Any questions about this? Okay. One last thing with this equal ripple filter. I need my textbook. Give me a second. Here we go. Here they give you the frequency response of the filter. H of omega is 0.2273 cosine omega cubed plus 0.5778 cosine omega squared plus 0.3505 cosine omega plus 0.0311. There's h of omega. So the first thing we want to do is get rid of the cubes. So h of omega then is 0.2273. What's cosine omega? Cosine omega, let's do squared first. Cosine squared, okay, it's cosine omega times cosine omega. It's a half plus a half cosine 2 omega. That's an identity. That's an identity you must know. So cosine omega cubed is going to be a half plus a half cosine 2 omega times cosine omega. So that's a half cosine omega plus a half cosine 2 omega times cosine omega. Again, you need identity there. That's going to be half cosine omega. And that's going to be plus a quarter cosine omega plus a quarter cosine 3 omega using the right identity. So cosine omega cubed is a quarter cosine 3 omega plus 3/4 cosine omega. So we put that here, a quarter cosine 3 omega plus 3/4 cosine omega. Plus 0.5778 times a half plus a half cosine 2 omega. See how your math, the math that you're supposed to know is coming in handy? So let's collect like terms. So that's a quarter times 0.2273. 0.2273 divided by 4. That's 0.056825 cosine 3 omega. Plus a half of that, 0.5778 divided by 2. Plus 0.2889 cosine 2 omega. Okay, so that takes care of that and that. And then what are we left with? We left with 3/4 times that plus this. So 3 divided by 4 times 0.2273. Okay, plus 0.3505 equals plus 0.520975 cosine omega. And now the constant, half of that plus that, plus 0.5778 divided by 2 plus 0.0311. And that's plus 0.32. So that's what h of omega is. That's h of omega. That's how we get h of omega. Now what? How we can get h of n? How we can get the impulse response? Because that's what we need. Nobody has any ideas?
Do we need to find omega and substitute it in the equation or it's somehow?
What do you mean find omega? Omega here is not a value. omega here is values between 0 and pi. This is the frequency response. There is only one value of omega if you have just one sine wave. But where does the problem say that? How do you find the frequency response? How do you find the impulse response for the frequency response? Let's take a simple problem first. If I give you h of omega, let's take the more. Some number. I'm going to call it 2. 2 divided e j omega. That's a homework. Except this number here, it would be different for each person. How do we find h of n? Nobody?
Maybe we could break it down a little bit by saying h of omega equal y of omega over x of omega.
All right. I don't know how that helps, but let's do that. So y omega of x of omega equals 2 ej omega, yes?
Did we convert? Okay, the next step would be like 2 over cosine omega plus sine omega.
How does that help?
I think I know how you find it.
Yes, Mr. Johnson, let's hear from you.
H of n, which is the impulse response, equals z inverse of h of z. And h of omega, in order to find h of omega, you would have h of z. So could we reconvert h of omega back to h of z? And this
All right, let's do that.
inverse, yeah.
So let's find h of z. And what is h of z, Mr. Johnson?
That'd be 2 over z.
2 over z. Or 2 times z to the negative 1.
Yes.
All right, how does that help?
And I think we have to find the z inverse of that.
Well, how are we going to do that?
Or the z transforms.
The z transform? It's already in z. It's already in the z domain. You're not going to use the z transform for anything.
So would it be h of n equals 2 sine open bracket n minus 1 or something like that?
Don't you have to find
I don't know why you're guessing. You should know the answer to this since 320. Well, we didn't call it h of z then. We call it h of s then.
so that'll be the inverse?
So
The inverse of what?
The inverse.
sorry, let me try.
Let Tori go.
All right, my bad. Would it be 2x open bracket n minus 1? That'd be
Yo, man, what are you trying to take the inverse of? I don't see any x in this equation. Where you get an x from? The transfer function, the impulse response, how are these related? How are these related?
H of n is equal to the z inverse of h of z.
Thank you very much. Z inverse of 2, z negative 1. You can bring up 2, z inverse of z to negative 1. What's the inverse of z to negative 1?
That's delta n minus 1. Delta of n minus 1.
2 times delta of n minus 1. So we'd plot h of n. If we'd plot h of n, this would be 0 and this would be 1. This is n. And this is h of n. And this is 2. And so your difference equation, h of n equals 2 delta n minus 1, your difference equation is y of n equals 2 x of n minus 1. This is your difference equation. So what's your output? Is x of n is x of n minus 1. So your output is simply y equals x of n minus 1. And of course, you need a 2 here. There's your filter right there. There's your memory. And you need, of course, you need gain here of 2. There's your filter right there. All right. I hope you notice what we did. We went from omega to the z domain. That's what we did. We went from omega to the z domain. Okay. Let me remind you what's happening. Okay, I may have to reboot my document camera since it's playing fool. All right, give me a second. Just a reminder. I don't know why it's playing full. How do I convert that? How do I convert that to the C domain?
You showing your screen?
I don't see nothing.
Okay.
I don't see none on the screen.
Give me a second. How about now?
Yes, sir.
Okay. How do I convert that H and Z?
It will have to be in the form of h of e to the j omega first, right?
Yes. So what's cosine x in terms of what's cosine x in terms of e to jx? Well, it's an identity that you've been taught, but clearly not an identity you have remembered. Cosine x is e to the jx minus e to the minus jx over 2. So we just put omega there. We're good.
Your screen jumping a little bit. I know you noticed.
I know I may have to reboot the whole computer. I'm hoping that'll clear it up.
I mean, it's good for now.
So that means cosine 2 omega is e to the j 2 omega minus e to the minus j 2 omega over 2. That means cosine 3 omega is e to the j 3 omega minus e to the minus j 3 omega over 2.
You want to show us this in 320, right?
Yes. Yes, I did. Well, not these two, but these two just fall from that. I showed you this, the 320. And likewise, sine omega, we don't need it for this problem, but sine omega is, sorry, positive. It's a positive, sorry. E to the jx minus e to the j omega minus e to the minus j omega over 2j. So we put these into here. And that'll give us an equation for with e to j 3 omega, e to j 2 omega, and e to j omega. And then of course we'll use z equals to e to j omega, z to the negative 1 equals e to the minus j omega. Okay, z squared equals e to j 2 omega, z to the negative 2 equals e to the minus j 2 omega. and z cubed equals e to the j3 omega, and z to the negative 3 equals e to the minus j3 omega. So let's do that. So h of z becomes 0.056825 e to the j3 omega plus e to the minus j3 omega over 2 plus 0.2889 e to the j2 omega plus e to the minus j2 omega over 2 plus 0.520975 e to the j omega plus e to the minus j omega over 2 plus 0.32. Okay. So we have, take the 2 out, 0.056825 divided by 2, 0.02, 0.0284 times z cubed plus z to the negative 3 plus 0.2889 divided by 2, 0.14445 z squared plus z to the negative 2 plus, oh, never mind, wrong place, 0.520975 divided by 2, 0.26049 z plus z to the negative 1 plus 0.32. There's your h of z. There's your h of z. And if you have a h of z, then you have a h of n. So your h of n is 0.028412125. What's the inverse of z cubed? What's the inverse of z cubed?
Would not be 1 over z to the power negative 3?
And how does that help? How does that help?
Is it delta? Yeah, delta open bracket n minus 3.
No, that's what this is.
What if you put a plus?
Yes, delta of n plus 3
Okay.
plus delta of n minus 3. Plus 0.14445 of delta n plus 2 minus delta of n minus 2. Okay. And then it'd be plus 0.14445. No,
Delta n.
yeah. Plus 0.6049. Okay. Delta of n plus 1 plus delta of n minus 1 plus 0.32 delta of n. And if we plot, if we were to plot that,
I got it then.
if we were to plot that, then we'll see this. We'll see this 0.32. This is 1. This is negative 1. This here is 0.26049. And then we'll have, see it's symmetrical? See how symmetrical it is? And this point here, point 14445. And then the third one, there's n. Okay. The third one is 0.0284125. And there's h of n. Notice the symmetry. I'm going to have to reboot my whole computer before my next class because I don't know why my document camera is going crazy. Now think about what this is saying, folks. What is it saying my input is? What's my input? What is my input?
I assume my input is the impulse.
An impulse. So where impulse where? An impulse where? An impulse at what time, Mr. Johnson?
Out of a pi?
At pi? An input at pi? What does that even mean?
I was thinking with the 0 and pi, the minimum maximum thing, something like that.
The impulse is at n equals 0. This is the input. This is x of n. When the input is an impulse at n equals 0, this is the output you get. This is the output you get. Anybody see anything wrong with this? Anybody see anything wrong with that?
So, Dr. Carter, I have a question.
Yeah, go ahead.
Did you choose that point because it is very similar, what you call it? Symmetrical?
Uh,
The H of n equals 0.
H of n, that's what the math says. That says if you wanted that transfer function that we began with on page 4. Let's remember how this work. Let's work out how this happened. If you want the transfer function on page 4, this is the impulse response we need. But does anybody see anything wrong with this? Look at the bottom graph. Look at what the bottom graph is saying. We are implying an impulse at n equals 0, but yet the output exists before we apply the impulse.
Yeah, that's different from what you were showing us at the beginning of class.
This is called anti-causal filter. In other words, it can't exist in nature. You can't have an output before input's applied. So in other words, we really cannot create that frequency response I gave you on page 4. Because if we use that page 4, if we use the frequency response on page 4, we will have this anti-causal impulse response. Now, what we can do is shift everything to the right. We shift everything to the right and create a causal filter. So we would have what I showed you earlier. So what do we have to do to that to get this? Because this we could deal with this. This is causal. What do we have to do with that to get this?
We delay it somehow.
Yes, and how do we create delay? How do we create delay? We delay it by 3. -3 becomes 0. So we have to multiply. We have to multiply h of z by z to the -3. We have to multiply h of z by z to the -3 because you see we want to make z cubed. We want to make that z to the power of 0. And then all of these, that becomes 0. Okay? That becomes -6. 0, 1, 2, 3, 4, 5, 6. This becomes z to the -2, z to the -4, z to the -1, z to the -5. So we create a causal filter by passing h of n through a delay. Remember, this is the delay. That's the delay of 3. That's z to the -1 times z to the -1 times z to the -1. So we pass this h of n. We pass this h of n. And out here we'll get h of n minus 3. and h of n minus 3 is causal. Any questions about that? So we can't create exactly. We can't create exactly the frequency response we have on 4, but we could pass that signal through a delay, and delay does not change the magnitude response. A delay just changes the phase response. What's the phase of this? What's the phase of this filter? If I asked you to calculate the phase of that filter, what would the answer be? Wow.
0?
Yes. Yes, exactly. This is a zero phase filter. Why? There's no complex number. This is all real numbers. The phase of a real number is 0 or 180. If this becomes negative anywhere, the phase could become negative. Could become 180. This is 0 or 180. So what this is saying then, a zero phase filter cannot exist, because that would mean h of n is anti-causal. But if we put this filter through a delay of 3, we can create that filter, but the phase now would be linear, but the phase won't be 0. Any questions about that? So you create linear phase, but you can't create 0 phase. Yeah. Before I say goodbye, any further questions? Again, let me say, and every one of my classes is always lots of information. And if you don't study that information, then you don't learn it. And you never know what will crop up on the final exam. All right. I'll see you on Wednesday, Lord willing.